So you're saying that at the point, so the point right here, what is happening?
It's more like it's straight. It's not really a curve.
So it's straight. It's not that curve thing. So, and that's a really critical piece that we will talk about. I'll come back to that one here shortly. Parker, what's something else that you observed on that graph?
I didn't really find anything else.
Nothing else? Okay. Logan? Both lines meet? So at the distance right here, okay, that point that Kenneth had pointed out, that both of those lines are going to meet up. Okay, I would agree with that. Elijah, you had some other small observation on there. Do you mind sharing one of yours?
I just said at 0 minutes he's at 6 blocks.
At 0 minutes, he's at 6 blocks. Are we all good with that?
Yes.
Okay. There's some key information there. Carson? There is a domain and range. Yep. Renee? Goes down to 0 blocks, ends up going back up again. Okay, absolutely. Any other observations that we should be making note of here? Here's some key stuff. We don't need to be on devices to do it, though. Okay. So I want to be able to go back to what Kenneth had pointed out here is this whole idea of the U shape as opposed to this V shape graph. In the past few months, we've been working with quadratics. We've been talking about parabolas and a U shape or an N shaped curve, where we were saying going over 1, up 1, over 2, up 4, over 3, up 9, and this graph curved. Okay, it looks something along those lines. Now, it's going straight V. It's going down then up again. And this is why I was so particular about how the graphs looked when you would draw the graphs out. Because now, these are two completely different graph representations. And you're going to see that here in a little bit. You will probably want your blue sheet to be able to take some just straight up notes here shortly. I'll give you a chance to get that out. Not just yet, but you can get out the blue sheet, but we're not going to take the notes just yet. It's really here coming up for problem number 3. So for problem 2, we're going to come up with the piecewise function for this particular situation about Michelle and the bike ride that she is on. So the first one that we have is this downslope, where we're talking about from here to here. Okay, Michelle is going on this bike ride to her favorite lake. How far away is she from her lake, from her favorite lake? 6 blocks. And how long does it take for her to travel to her favorite lake? 3 minutes. Okay, being able to see there. And how long is her trip in total? 6 minutes. So just some key pieces of information that we need to know about in order to kind of really conceptualize what's happening. So the piecewise part of this, we can say f of x equals, and we can break it up into pieces. So for the first piece, and we're going to put this into point-slope form. If you don't remember point-slope form, we talked briefly about it last week. We said that this is y equals m times x minus x1 plus y1. I'll give you a chance to jot that down. That might go into your blue sheet just as a reminder. And if you're looking at this like, man, I've never seen this before. This is a whole lot like vertex form of a quadratic equation. So this x1, y1 seems like this mysterious thing that we're just adding in. Here's basically all it's saying. Pick a point, any point on the line, and I can give you an equation for that line. So x1 is the x-coordinate, y1 is the y-coordinate. And from there, I should be able to come up with the line. That's the general equation for point slope form. Okay? So for the equation for this line right here, the segment, the first one, what is the slope of that first segment? Taking a look at it, I need to know what the slope of that segment is. Anybody think they've got it? Naya, go ahead. Right one down 2. So we actually go the vertical change first. So we'll say that would be a positive or a negative? Positive. If it's going down, what would it be? Negative. So it's going down 2 and right 1. Well, I don't need to put this as negative 2 over 1. So I'll just leave it as negative 2. Then I need a point, any point on this line. I'm going to end up taking this point right here at the y-axis. What is the coordinate for that point? 0, 6. Yeah, it's 0, 6. So we'll plug that into the equation. Y equals m times x minus x1 plus y1. So we'll take x minus 0, that's the x portion of the coordinate, plus 6, which is the y portion of the coordinate. Your x1 and y1. But this thing is not going on forever and ever and ever. We have a domain restriction. Where does this equation start? 0. And where does it end? For this portion of the equation, where does it end? 3. Hey, it goes from 0 to 3. Okay, we're looking at the domain. So we're looking at all the x values that I can use. This equation is telling me I can use 0, 1, 2, and then it has to stop at 3. So let's check the second part of the equation. Okay, this piecewise function that we're messing with. We look at the second part, and we would end up having a little bit different stuff going on. But what is the slope for the rest of this v? How is it moving? So not the same. Up 2, right 1. Up 2, right 1. Up 2, right 1. So what's the slope? 2. And then I can pick any point on this line to be able to go from there. I'll take where it starts at 3, 0. So I'll have x minus 3 plus 0. And if you remember from last week, we were talking about domain. We were talking about the different equations. You're like, wait a minute, this 3 goes right here. Oh, this 0 goes over here. And there are some relationships that we know about for these equations. So what is my domain going to be for the second equation here, for this portion of Michelle's bike ride? Jason? So I'll agree with x is less than or equal to 6. But yep, it starts at 3 and goes to 6. Okay, and the big thing here is that it's 3 is less than 6, not 3 is less than or equal to, because it's already included here. Okay, we include it in one equation, not both. So we'll need to make sure that we know, okay, it's included, the 3 is included in the first equation, not in the second one. Okay. And now we've got a piecewise function. So for the people who have not been here intermittently or maybe missed the whole time, this is a piecewise function. Okay, that's what's happening here. We're taking an entire graph and we're breaking it up into pieces. That's why it's called a piecewise function. Okay? We good there? All right, let's move ahead. This is the part where having that blue sheet is going to be helpful. What I'd like for you to do is to, on your blue sheet, on the back side where you've got some space to write, to jot down a linear absolute value function. And we're just going to take some straight up notes about what a linear absolute value function is. So first, what are some things that are happening looking at this graph? What are some characteristics about the graph that you see here that might be kind of important? Logan? At 0, it immediately starts decreasing. Okay? Good. Renee?
The distance always stays the same. Or not the distance, but like the time will always stay evened out. We like within 3 or this or say 0.2468, remains constant.
So the timing will be evenly spaced out?
Yeah.
Okay. Any other noticings that you have about this, just in general, a linear absolute value function? That's what this is. This is a linear absolute value function. And if you remember, last week we were talking about absolute value functions, and this is really where it starts to play into tying everything together. Logan? Is it always going to be the starting point and ending point? Could I have changed it? I could have continued that on. But in this case, yeah, that works. Elizabeth? It's a V instead of a U. All right, so here are some things that people have said throughout the day. All outputs are going to be positive. If you look at that, all the outputs are positive, which, going back to what we did yesterday, should make some sense. Or not yesterday, but last week, should make some sense, because if you think about the outputs, when I take the absolute value of any number, what is it always going to become? Positive, yeah. The absolute value of any number is going to be positive. So all outputs are going to be positive. The second part, it looks like an A. Looks like a V. So the graph of an absolute value function, a linear absolute value function, will look like a V. A special because one of them is squared and this one is not. So with the quadratic, it's curved because there's a square, because it's not just going up a consistent amount. This one here is going up a consistent amount, up 2 over 1, up 2 over 1, up 2 over 1, or down 2 over 1, down 2 over 1. A quadratic is going over 1, up 1, over 2, up 4, over 3, up 9, and so on. Robert, is that helping? Okay. Then the third thing that I'd like for you to know about here is this piece, that the slopes are going to be opposite. The slopes of these lines are going to be opposite. Another way of putting this is that it reflects at a certain point. We good? We got all that? Yeah. Oh, you want a blue sheet? Yeah. All right. So let's go ahead and use this to be able to move on. You're going to see this here, and it's going to look really intense, possibly overwhelming. I want to be able to break this down. So we've got an example. F of x is equal to x. Whatever I plug in for x, that's what it equals. There you go. G of x is taking whatever the value is and finding the absolute value of that. Okay. You can do all of this. It's just a matter of this part right here seems like really intense. It's not as bad as it might look. So again, the function f of x, we're going to set equal to x. Then for g of x, we're going to take whatever the answer is and find the absolute value. What does that mean? We've got this table. So in your workbook, you've got the table there on the bottom of page 29, and we're going to fill this out. So this is how difficult this really needs to be. When I plug in -4 for x, I would get -4 for f of x. Right? Because f of x is equal to x. What do I get when I plug in -3? There you go. And you should be able to do the rest. It should be pretty straightforward. But now the hard part is going to be g of x. Well, g of x is saying, hey, take whatever you get for f of x and then find the absolute value of that. So what is the absolute value of -4? What is the absolute value of -3? Finish the table. You should have -2, -1, 0, 1, 2, 3, and 4. When you take the absolute value of all of these, you get 2, 1, 0, 1, 2, 3, and 4. You're taking the absolute value, which means it's just becoming positive. That's it. So where it's asking, explain how g of x affects the output values. What is g of x doing to all of the f of x values? Ben? Making it positive. That's it. So in the space there with number 4, I'd just like for you to jot down that it is turning all of those outputs positive. So now next, we're going to graph this. So we have the data, we have the x and y values, and we're going to try to graph these, try to figure out what's going on here. If you look at prompt 5, it's telling us first to graph f of x. And if you're stuck or confused, really, you're looking at the input and the output of each of those data points. So -4 went to -4, -3 went to -3, -2 to -2, -1 to -1, 0 to 0, and so on. Give you a chance to graph f of x. And it also says on there to use different colored pencils for each of those. I don't really care if you have a different color pencil. Maybe you've got a pen. Maybe you're just going to use the pencil. You're going to write one faint line and one dark line. Go for it. But the goal here is to be able to graph both of those functions, the f of x function and the g of x function, on the same coordinate grid. Give you a chance to do that. We'll come back and we'll talk about it. So I've gotten a chance to see some of your work, and I'm digging it. I want to be able to see it completed. I want to see lines that have been completed. So what I mean by that is that you've got your points and that you have a line going through all of those points. Okay, not just for the f of x function, you also have a label. Okay, this is my f of x. But that you also have the g of x function graphed and labeled. I'd like to be able to come by, take a look, and see what you have there. Go ahead. So we should have The f of x function is pretty well laid out. We're good there. It's the g of x that we start to get tripped up on because it's new, because we haven't done this before. So if you look at this one, when we remember making sure that we've got the arrows pointed in both of those directions, going into negative infinity and positive infinity, the g of x function, I'm going to put this into a different color just to make it easier for you to see the difference. It starts going down, and then it gets to that 0, and then it goes back up again in that other direction. It does not make a big X. It's going to make a Y. And the reason for it, why is the left side so different? What is happening on the left side of the equation here, or left side of the graph? If you look at your table, what did you do for all of these negative values? Why did you make them positive? What property or what thing were we doing to make all of those positive? Absolute value. So over here is where the absolute value is taking place. Yeah, that's where that flip is happening. Okay, we're taking this negative set of values, we're turning them positive by taking the absolute value of them. Okay, let me unmark that up. Got it. So you should have something like this. Now, what I don't want to see is that we are stopping our graph like right here. Like, all right, I'm good. That's good enough. No, I want to see it continue on. I want to make sure that we're using the graph paper that has been provided, or the grid that's been provided for us. Okay? All right. So next one is this here. And I've kind of gone through the difference in graphs already, so it'd be a way for you to process what that was. What we're going to do right now is actually write the piecewise function for g of x. So you have the graph there in front of you. I don't. And we're going to write the equations for g of x. Looking at that first part of the equation, okay, the left side of the graph, what is the slope of that graph? Not quite 1. What is the rate of change that's happening on the left side of the graph? -1. So we say -1x, or just -x. And where would that cross the y-axis? 0, 0, 0. So we would have a point, so we would be able to put in x minus 0 plus 0, but really that's just a whole lot of unnecessary work. We could just put it as y equals -x. What is the domain of the left side of the graph? What are the x values that I can use for this portion of the graph where it's -1x? Think about that. Not any number. I heard someone say it, negative infinity. Okay, I can use any negative number that I want all the way up until, when does this graph stop? Moving to the right, when does it stop? 0. So we would include the 0 in there. The next part, looking at the next graph. What is the slope of the graph on the right-hand side of that g of x function? How well is it moving? What is it doing each and every step? Going up by 1. So your slope would be 1, or just, we could write it as x. Remember, f of x equals x. And when does it start? 0. When does it stop? Positive infinity. So good question. Why wouldn't it be infinity both ways? Well, we got to go back and look at the piecewise function. We're just looking at this graph. This is a better copy how it says this. Good. They are the same shape. Yeah, we still have that same V shape that's going. Good. What is another similarity? Yes?
It's for the same with different numbers.
Same way, different numbers? Yes. What is another similarity? What is a difference? Hey, your choice there. A similarity or a difference, Jason? Negative infinity to positive, and the other one didn't, right? And the other one we had stopped it and started it at specific points. Okay? Good. Any other similarities or differences between Michelle and just this generic g of x? Yes?
The first one has a bigger slope.
First one had a bigger slope. Okay, whereas this one here, it's a little bit less of a slope. Okay, so a lot of different things that we can draw from and compare to for g of x and the equation that we wrote for Michelle. The last thing that I would like for you to do is to take a look at number 9. I don't have all of the prompts for number 9 on the screen. You have them on your paper. There are 6 of them. It's a matter of picking out what's important, what pieces we can draw from this information. The maximum, the minimum, the domain, the range. Okay, being able to pull apart this graph and this information and conceptualize what is actually happening. You've got about 3 minutes until we pack up, which should be enough time to get at least 3 of these done. Some of you will finish all, some of you will just get those 3. But the goal right now should be to try to answer as much of number 9 as you can. The domain, the range, the maximum, the minimum, and a couple other pieces for you to think about. Okay, we'll wrap up here in about 2.5 minutes. Go ahead.